verification and certification of EVM optimizations. This project is set out in the context of an optimizer, which is a program that takes a sequence of instructions and returns an optimized version, better than the original by some metric, and of a verifier, which is a program that takes two sequences of instructions and ensures that they are semantically equivalent. That is, that the effects of executing one are the same of executing the other. The verifier is developed in order for the optimizer to be more easily trusted. But that begs the question, if we develop the verifier in order for our users to trust on the optimizer, what makes our users trust in the verifier itself? The way we solve that problem in the Forbes project is through the use of the Coq programming language, which is both a programming language and a theorem prover that allows you to develop an algorithm and mathematically prove its correctness. The goals of the project were to develop and verify an implication checker, and do so modeling it in Coq so that it could be used from within the Forbes project. But what is an implication checker and what problems is it trying to solve? To answer this question, we need to talk about contextual information. In the field of program optimization, contextual information is key. Take a look at this snippet of code, for instance. You see that the green section can only be accessed through the if statement. What this means is that we can assume the condition in the if statement to be true in the green section. But if the condition is true, then the variables x0 and x1 differ by a value greater than the word size of the Ethereum virtual machine, which is 32. And therefore, the locations of memory which these two values are pointing to are disjoint. This allows us, in the green section, to reorder these memory accesses without actually changing the semantics of the code. The kind of information we're interested in to extract from our contextual, from our context, are those constraints which can be described or translated into octagonal constraints. Octagonal constraints come in two types, either additive or bound. X and Y represent integer variables, and Z is an integer constant. This is a common situation in which we would find ourselves in. The white constraints on the left are those obtained from the contextual information at one point in the program, usually given by some static analysis tool. And the condition on the right is the constraint that we need to be true in order to apply or verify a certain optimization. Take note that while these constraints are not octagonal constraints, they can be translated into octagonal constraints, which means that they're still valid constraints that our program can reason about. The way we would check whether the condition we want can be derived from the constraints we have is by picking any two conditions and combining them into a new valid condition and checking whether this valid condition can help us deduce the condition that we need. While doing so, we need to ensure that the conditions that we're left out with are valid. In this case, this wouldn't be a valid condition since there's a coefficient that is not 1 or minus 1 multiplying to our variable, but we could fix this by just moving that coefficient to the other side of the equation. In fact, since x1 is an integer variable, we could actually round down both sides of the inequality and get a stronger constraint than what we would have originally been able to deduce, which can be derived from the original list of constraints. And therefore, we've managed to get more information. While combining these over and over again, at some point we would hope to get a condition that implies that which we need. The way we implement this is encoded as a type in Coq. A conjugate implication checker is a record type with two fields. The first field is a function that takes a list of constraints, which we will call our hypothesis, and a constraint, which we will call our thesis, and returns a Boolean. If this Boolean is true, then it must be true that the hypothesis imply the thesis. And this condition is actually encoded as the second field of our type. We can do this since Coq is a theorem prover, and it allows us to explicitly write a theorem or a proposition as a type, where the elements of the proposition are actually the proofs that this proposition is true or not. This encoding allows us to perfectly mirror the original goals that we had about development and verification of implication checker. Therefore, in order to both develop and verify the implication checker, we only need to create an instance of this type. The way we did this in this project is through the following definition. The function returns true if there exists a constraint C prime in the transitive closure such that C prime trivially implies the thesis. By trivially implies, we mean that if the thesis was x greater than 0, then C prime would be something like x greater than 100. We have a stronger constraint than the thesis, and therefore the weaker constraint trivially falls from the stronger one. This whole implementation relies on whatever the transitive closure ends up being, which is computed by successively applying n times iterate the function over the hypothesis constraint. But what is the transitive closure? The transitive closure of a set are the strongest constraints which can be deduced from this list of constraints. Therefore, all of the thesis constraints which our function should return true to are those that can be trivially implied by our transitive closure, which is exactly how we have encoded our algorithm. The algorithm we've chosen to compute the transitive closure is based on Harvey-Stuckey's tightened transitive closure algorithm, which gives us a way to construct the set of constraints A prime, which when added to an already transitively closed set H, allows us to keep it transitively closed if we add another constraint C. That is, if we have a transitively closed set of constraints H, and we want to add a constraint C, then Harvey-Stuckey's tightened transitive closure algorithm tells us which other constraints A prime we need to add to still have the whole union be transitively closed. These new constraints are what the iterate function adds to the original hypothesis, and therefore after successive applications, we hope to get to the transitive closure. To do so, this is the implementation of iterate that we have in this project. The new constraints function will just get all of those constraints that need to be added in order to improve on the previous iteration. Flatten will just make sure that those constraints are tightened, and join will simply append these new constraints to the ones from the previous iteration, while also ensuring that no one constraint remains that is trivially implied by another one in the final list. We observe that we can actually understand this iterate function as the composition of join C, flatten, and the new constraints. This is going to be useful since in the verification we would need to use the following theorem. Iterate implication says that for every constraint in iterate of C, this constraint can be derived from C. To prove this, we will use the following auxiliary theorems, also proven in the project, and unfold the definition of iterate into its composition of different functions, and use successively these auxiliary theorems to deduce that iterate implication will only be true if the C constraints can be derived from C itself. This is actually the reflexivity of implication, and therefore we know it to be true, which concludes that the iterate implication theorem is true. To prove the soundness of our original algorithm, we make use of the fact that the conjugate implication checker function has returned true for some hypothesis TS and for some thesis C, which means that there must exist a constraint C prime in the transitive closure such that C prime trivially implies C. Then we prove that the hypothesis implies the thesis through transitivity by first applying the iterate implication theorem inductively to prove that actually our hypothesis implied the transitive closure of the hypothesis, and by later on applying the fact that our function returned true to see that the transitive closure implies C prime, and that C prime trivially implies C, and therefore C prime implies C. By transitivity, we get what we wanted. Let's look at how this would look in code, how we would use this kind of algorithm. And to do so, we're going to use the constraint that we had in our example before, but actually transform them into abnormal constraints, since our algorithm expects all constraints to be in this form. This is how the definition, how this example would look like in Coq. On the first line, this local definition, this implication checker, is just a function that constructs the conjugate transitive closure checker and calls its function member on the hypothesis. The next two local definitions are just our variables or constants for the hypothesis and the thesis. On the final line in the compute statement, we're asking Coq to evaluate the expression implication checker on our hypothesis and our thesis. If we give this to Coq to execute, we observe on the right that it returns true. Therefore, it was able to derive from our hypothesis that the thesis. Therefore, it was able to derive the thesis from our hypothesis. In conclusion, we were able to model the problem in Coq and develop and verify the implication checker. Furthermore, personally, I wanted to learn more about software verification in Coq, and I think that the Forbes project presented itself as a perfect opportunity to do so. In terms of future work, we have yet to use the implication checker in Forbes 2. The theories are developed, but we haven't connected them to the rest of the project yet. As for future work, we still haven't used this implication checker from within Forbes. Although the integration to the rest of the code is already made, which means that this piece of code can already be used by other parts of the project, we still haven't gotten to the point where we have used it. Therefore, we don't have any metrics to show what improvements or what usage or what impact this had on the project itself. Furthermore, we could always try to improve the efficiency on the transitive closure algorithm. Although Harvey's and Stuckey's tight and transitive closure algorithm was really useful for our purposes, since it's relatively simple, which makes it easier for us to reason on it. There are better algorithms with a better runtime, which we could use. This was never a hard requirement on the project, since the constraints that we're working on are relatively bounded, and therefore runtime of the algorithm is not something that was super high in our priority list. But therefore, it's still something that we could consider. Finally, with all the theories that we developed in this project, it would also be possible to try and implement a satisfiability checker. The theorem that we have, the condition that we have imposed on our implication checkers are the soundness of the algorithm. But if we also have the completeness, that is, if our function returns false, then it must be true that our thesis cannot be derived from our hypothesis. Then we could implement a satisfiability checker by just checking whether our function returns false when we give it a constraint that is unfeasible, something like 0 less than equal to -1. That's it for this presentation. Thank you very much for listening, and all files are available in GitHub.